Alright, welcome to 2.2 part 2. To kick things off, I want to show you a little bit of a little bit of a video clip from one of Mr. Martin's lessons, just because there's kind of a cool intro to this on the using the graphs for the sine and cosine and why they are the derivatives that they are. So let me show you that real quick, and then I'll kind of pick up here where these don't quite fit our notes, but that's okay. So let me show you this first.
Differentiation rules and rates of change. Theorem 2.6 talks about the derivative of the sine of x and the derivative of the cosine of x, both with respect to x. So to examine these, let's take a look at the graph of first the graph of y equals the sine of x. You can see here that we've got this point P on the curve y equals the sine of x, and we've got a tangent line through P, and you can see that the slope of that tangent line obviously changes as x moves to the right or left right here. So we want to come up with a graph whose y values, f prime, are the slopes of those derivatives, okay, the slope of the tangent line equal to the derivatives. So if we slide along to the right here, and if we were to show the value of f prime, you can see this green dot here goes up and down, just like the slope of the tangent line. There is 0, and now it's all negative, and now it's 0 again, and then it goes back to positive. And so you can see at any point along here, if we move x over to here, the slope of the tangent line is 0, just like the y-coordinate is 0. Okay, the y-coordinate of f prime, I should say. The slope of the tangent line there is about -1, and the y-coordinate of the green dot is -1. The slope here is 0 again, approximately, and the y-coordinate of the green dot is also 0. And from here to here, those slopes are all positive. From here to here, they're positive and increasing, and then from here to here, they're positive and decreasing. So watch this green dot. From here to here, the green dot is a positive y value and getting bigger, and then from here to here, the y value of the green dot is still positive, but getting smaller as it approaches 0, and then the same thing happens as we go to the right. And if you go ahead and continue to slide that along, and you actually show the graph of y equals f prime as its own single graph, you can see that the slopes of the tangent lines of the blue graph, the sine of x, give you the graph of y equals the cosine of x. So what we've just examined then is this part right here, which tells us that the derivative of the sine of x is the cosine of x. Okay, and likewise, let's take a look at what the derivative of the cosine is. Forget about this blue line now. Let's look at the green line. Imagine that the green line were your original graph. Okay, well, we can show the derivative of that one here. That's called f double prime. It's the second derivative of f, and the first derivative of f prime. So take a look at this pink dot here as we slide x along to the right, and how it relates to the slope of the green line. Well, right there, okay, let me move this over here. Right there, the slope of the green line is 0, and so the f double prime is at 0. Right here, the slope of the green line is 0, so f double prime, the pink dot, is at 0. And you can see, likewise, these values here, the slope of the green curve from here to here are all negative, so the y values of the pink dot are all negative. Same thing from, say, here to here, the slope of the green curve is positive. It goes from 0, increasing. Now it's at its highest point. The slope and the slope of the green curve and the y-coordinate of the pink dot are both at their highest point, and now they're both still positive but decreasing and getting closer to 0. So if you were to slide that along and then show what that graph gives you, again, ignore the blue curve, look at the green curve here. That green curve is y equals the cosine of x, and it's mapped to its derivative, which is the pink curve. And what can you say about the equation for the pink curve? Okay, well, now find the relationship between the pink and the blue. If the blue is the sine of x, reflect that in the x-axis, and the pink curve's function is y equals negative sine of x. So what we just saw here then is that the derivative of the cosine is the negative sine of x. Guys, this is one of the most commonly missed problems throughout this course, just because the negative sign throws us off and it's hard to remember which is which. The derivative of the sine is the cosine. The derivative of the cosine is the opposite of the sine of x.
Right, I'm going to pick up where those things left off. But a cool video, so I wanted you guys to see that part. Anyway, moving on from there. So those are two super important rules that you guys got to remember. So derivative of sine is cosine, and you got this one right over here. Just don't forget the negative whenever you take the derivative of cosine. Derivative of e to the x is e to the x. The reason this is shown here is because if there is something more than just x right there, we would have to take the derivative of that interior function and we multiply it times e to the x, so it ends up going right here. And so we'll get some examples on that when we get there. But the main thing to remember on derivative of e to the x is e to the x, right? It is the derivative of itself. So a couple examples. If we were going to do the sine of x over 2, what's the derivative of that? Remember, for those guys, you could separate out that 2 and write it this way: 1/2 sine of x. And so we know the 1/2 is going to stay as our leading coefficient. So we differentiate the sine of x, which we just found out is the cosine of x. And so we have our derivative right there. Whenever you have multiple terms, just do one at a time, just go on down the line. So I'm going to start by differentiating this first term, multiply the 2 to the front. This becomes a 1. And so you get the first term, which looks like this. Then we're going to say the derivative of cosine of x is the negative sine of x. So you have a minus the negative sine of x. So that double negative creates a plus on that one. Go down to this guy. As I just showed you, the derivative of e to the x is e to the x. So this entire first term is going to stay just as you see it. Moving on to your second term, the derivative of cosine is negative sine. So you're looking at negative 4 times negative sine x, which becomes this term right here. And then the last one, remember, if you see a square root, you want to write that as x to the 1/2. And you would multiply the 1/2 to the front and then subtract 1 from the 1/2, and it would become this term right here. So kind of multiple rules getting thrown into one there. All right, slope of a tangent line. So we have our f of x or f of theta right there, and they're telling us what that equals. And so you could always write those in terms of x if that's makes more sense to you or not. We can write it in any variable, whether it's a theta or an x or whatever. And so we're given an ordered pair right here. So there's our x, there's our y. First things first, we want to find the derivative. So anytime you're trying to find a slope, step number 1 is going to be get the derivative, because the derivative function, remember, is your slope function. So we need that guy first. So if this is our function and we take the derivative of this, so again, we just said derivative of cosine is negative sine. So you get this look right here. And then the derivative of the x would be 1. And so here is our derivative, our slope function. Now we can plug in the x coordinate into our derivative function in order to get the slope. So we put the pi halves in for theta, and then we clean that up, and you have your slope at that point. Do keep in mind, if the y coordinate was not given, typically what we do is we take the x and we plug it into the original function in order to get a y coordinate. So you may run into some of that stuff too. So let me jump down to example 5. So looking now for the equation of a tangent line, keep in mind for this, we're looking at typically using point slope formula when you want the equation of a line. So y minus the y coordinate equals our slope times x minus the x coordinate. Okay, so up above they gave us, this is all the information from the previous problem. So we found our slope, so that's now going in for m. They gave us the they gave us the y and the x coordinates. And so we're just subbing those in. And you could always clean this up a little bit, of course, to put it into like y equals mx plus b type form. I can show you how to do this on a calculator. And all we have to do on that is take the original function, which was this guy right here, and we're going to graph that. So if you want to follow along here, based on those, you can tell that we're going to be in radians for this because it's in terms of pi. So make sure that you're in radians. So I'm going to go to my y equals, and we're going to do 2 cosine x minus x. So that's what it should look like. Hold on, let me change the lighting for you real quick. I think that'll help you see my calculator a little bit better. So there's our graph. For my window on this, I think those will be okay. Let's try that. So I'm going to hit graph. And so here's what we get. Sorry about the glare. There you go. So there's our graph. So if I want the equation of a tangent line, all I need to know for that is the x coordinate. Do keep in mind when we get this equation, it's not going to look exactly like this because it's not going to be in terms of pi. These are going to be decimals. Okay, so it'll be in terms of decimals instead of in terms of pi. But that's okay. It's still the same equation. It's just in decimals instead of exact form. So anyway, so right here under draw, it's in blue. So I have to hit second and then draw and go down to option 5 that says tangent and hit enter. And again, all you have to type in is the x coordinate. So I'm going to type in pi over 2. So second pi divided by 2 and hit enter. And it's not only going to draw it for us, so there's our tangent line, but it also gives us the equation of that line. Of course, it's in y equals mx plus b form. And you do have to interpret this a little bit here. So obviously, if you look at your slope, even though it says negative 2.99 forever, obviously that's negative 3. So sometimes you do have to interpret what that's giving you a little bit. We already know the slope is negative 3, so we know that's going to be our slope of negative 3 plus our y-intercept right there, which you can see is our 3.14. So again, if you were to put this into y equals mx plus b form, this is what it would look like, right? But we'd have obviously a little bit prettier numbers right there. So that's one way you could always get the equation of a tangent line. It's also the way of getting a slope. That guy right there is also a way of getting a slope if you know your x coordinate of the function, right? So we can get that from this as well. So let me flip the page for you. All right, so horizontal tangent lines, as soon as you see the word horizontal, automatically you know that the slope is 0. So if the slope is 0, that means your derivative equals 0, and that's how we're going to solve for x. So we're given this original function here, so we need to start by just finding the derivative of that, which would be this line right here. Again, the derivative of e to the x is e to the x, so nothing new right here. You got negative 6 for that first term. If I'm looking for horizontal tangent lines, then again, I know that my derivative equals 0, and that's the equation I have to solve in solving for x. So add the 6 over. I took the natural log of, added the 6 divided by 2. Then I took the natural log of both sides, and going to come out looking like this. So I'm going to leave it like this so that it's in exact form as my x value. Right, and so you can see that one right there. So I'm looking for coordinates, which means I also need the y value that goes with it. So I'm taking my natural log of 3 as my x value, plugging it into the original function there and there in order to get my y coordinate. And we're just simplifying this as much as we can. Don't forget you have this rule over here, that e raised to the natural log of anything is that item. So that was just an old Algebra 2 log rule that you would have learned. We've seen that this year already as well. So that's where this guy is coming from. And that's it. That's really as far as it could go without a calculator. And so that could be our ordered pair if we were going to write those in exact form, or if we didn't have a calculator to use. Right? This is as far as we could take it. One thing to keep in mind on this, because this is a common mistake, is whenever you are looking for a y coordinate, you will never, ever, ever get that from the derivative, right? A y coordinate can only come from the original function. So really, really important that you remember on this that anytime I plug in x into the original, I get a y coordinate. Anytime I plug x into a derivative, I get a slope, right? So two big differences on that. So let me jump down to example 7. All right, so same question. I'm still looking for the coordinates at horizontal tangent lines, which means again my slope would be 0 at those points because it's a horizontal tangent line. So again, I'm going to find my derivative. So here's our new rule that we looked at today. So remember the derivative of sine is cosine of x. And so if you take the derivative of this, we get this. Again, because it's a horizontal tangent line, I'm going to set my derivative equal to 0, and then we are solving that for x. So just a basic trig equation that we are solving. Subtract the 1, divide by rad 2, take the inverse cosine function in order to solve for x. So we're saying the cosine of what angle is equal to negative rad 2 over 2, and that would occur at those two values right there. Remember, I'm going to limit it to only those two because I was given this domain, so I can only keep the values that would fall within one unit circle. So that would be those two right there. So for these guys, those are my two x coordinates, and so now I need to take those and take turns plugging them into the original equation in order to get y coordinates. Right, and then of course it'd be best to write those as ordered pairs. So when you take 3 pi over 4 and plug that into the original equation up top, once you clean that up, you get this. This would be as far as it could simplify, and so we're going to keep this as our y coordinate that goes with it. And then you did the same thing with 5 pi over 4, and we're just simplifying that as much as it could go. And so those would be our ordered pairs. And then last thing, and we can end on this, is when you look at these two functions, how do you know which one is the original function and which graph represents the derivative? One super obvious way you could tell on this is the original function would be the higher exponent, because remember, whenever you take a derivative, you subtract one from the exponent. So if my original function was a quadratic, right, it was x to the second, well, when I take the derivative, that's going to drop down to x to the first, which would be a linear function, right? And so there's this linear function represents the graph of the derivative function, and then this had to be the original. Same thing on this one. Again, I can see this would have to be x to the third, would be that graph right there. I can see this would be an x to the second, so the one with the higher power is going to have to be the original, and then when you took the derivative of this and subtract one from the exponent, that dropped it down to x squared, which is where that one came from. All right, so I could tell that one would have to be a derivative function. And that is it for part 2.